Hi, everybody. I want to welcome you to this event organized by the American Nuclear Society's Risk-Informed, Performance-Based Principles and Policy Committee. That's RP3C, we call it. My name is Prasad Kadambi, and I chair the RP3C committee. The purpose of RP3C is to help modernize ANS standards. Modernization has come to mean that risk-informed and performance-based methods are employed to overcome the difficulties that we all have encountered with purely deterministic and prescriptive approaches and methods. We've been calling these approaches and methods RIPB for short. The Nuclear Energy Innovation and Modernization Act specifically mentions RIPB. If you look around, you will find it hard to find any place other than ANS, outside of NRC, of course, that has as much information and guidance at this point on RIPB. Overall, there is a lot of guidance available on RIPB, but most people have not had reason to become familiar with this information. This is primarily because the conventional approaches still dominate most things we do, including standards development. RP3C has been having these community of practice events regarding RIPB and associated methods, such as systems engineering, to enable practitioners to share their knowledge and experience. We've been scheduling these sessions for the last Friday of each month. Today, we will hear from Dr. Kent Welter of NuScale, almost to the day 1 year after the very first community of practice session with which we began these events in 2020 February. And at that time also, Kent spoke about systems engineering. We've been using that term and we've become familiar with how different people have been using that. I requested Kent to come back and 1 year on sort of go over why we are finding it more important to become familiar and use systems engineering approaches. So Kent, would you take it away, please?
Yeah, thank you very much, Prasad, for inviting me to speak today on our, I guess, 1 year anniversary of this community of practice. As Prasad mentioned, my name is Kent Welter. I'm a chief engineer, testing and analysis at NuScale Power. Next slide, please. NuScale's mission is to provide scalable advanced nuclear technology for production of electricity, heat, and clean water to improve the quality of life for people around the world. And we will achieve this mission by providing technology that is smarter, cleaner, safer, and cost competitive. Next slide, please. Agenda for today, go just briefly over NuScale technology and our development and deployment status. Then jump into an introduction to systems engineering, very briefly what it is. Also talk about value proposition of systems engineering generally, and then within NuScale, how we determined its value proposition for our projects. And then talk about how at NuScale we've tailored and implemented our systems engineering processes, and then summary and conclusions. Next slide, please. Very briefly, and there's a lot more information that can be found at nuscalepower.com. Previous slide, please. Sorry, I might have. Thank you. The NuScale Power Module is what's called an integral pressurized water reactor. It includes the reactor vessel, the steam generators, the pressurizer, and the containment all in one single package, if you will. It is a natural circulation reactor. It eliminates reactor coolant pumps and any large primary system piping. We recently went through a power upgrade, and each module produces up to 77 megawatts electric. And the size of these power modules are such that they can be built in a factory and then shipped easily for installation at a site. So the modules can be put into different size reactor buildings. We recently got a certification for 12 module reactors, standard plant design in the US, but we have smaller power plant solutions available as well, such as a 4 and a 6 module. Next slide. This is just an artist's rendition of the NuScale power plant, and then just speaking again to the different product offerings that we have to date. Next slide, please. This is a simple chart that shows how on the top left there, number 1, where power modules can be factory fabricated and then shipped to a site and installed to meet the power demands of our customers. Next slide. To get a feel for how far we've come and how far we have left to go for first plant deployment, this is an illustration of blazing the trail to commercialization. There's been about $1 billion US invested to date in development and deployment and licensing and certification of the technology. As I said, we've received NRC certification last year on a 12 module reference plant. We are working on developing the necessary packages for long lead time procurement in the next couple of years. I'll show a couple slides on that. And so we are, from a systems engineering perspective, I'll be talking about it, but we're going from the left side of the V and into the right side of the V where we're starting to produce parts and manufacture and build things. Next slide, please. This just shows our first deployment in the US, where we're working with UAMPS, that's Utah Associated Municipal Power Systems, to provide power for their customers and locating a NuScale plant at the Idaho National Lab site. Next slide, please. This shows a timeline of that deployment at Idaho. It's called the Carbon Free Power Project. Site characterization began last year, and that will continue on for the next couple of years. And we hope to mobilize construction in 2024 with the first module installed in 2029 and full operation in 2030. Next slide, please. This just goes and shows that where we are in the development process. We're working with our manufacturers for the power modules and the long lead time items, doing manufacturing trials and automated manufacturing ways that we can speed up the manufacturing process, because we're building multiple of these power modules, and so there's a production curve that we're working on with our suppliers right now. Next slide. Okay. So with the introduction to NuScale and where we are and sort of for the first plant in the product lifecycle phases, what is systems engineering? Well, in the simplest way, systems engineering is a proven set of tools and techniques just for managing the complexity of large projects and products with the goal to control costs, schedule, and quality. This figure on the left here is the Arcadia model-based systems engineering method. This shows how there are methodologies and tools to take large projects and products and develop requirements, develop different views on how they're going to operate, and how to structure the requirements and the products in a meaningful way, such that as designers, when we take a large complex thing and need to break it up into smaller pieces to then design it within different groups or disciplines, how to put it all back together so that it works as intended at the end. I actually did give a presentation, I think, towards the middle of last year on NuScale's model-based systems engineering pilot that we did. I think that was at an ANS meeting, and I think I have that available for folks if they're interested. But again, really, it's just a proven set of tools and techniques for managing the complexity of large projects or products. Next slide, please. An important aspect of systems engineering development and programs are systems thinking and the V development model. Now, there are different versions of the V development model, and there's even W development models. There's different ways to look at it, but it really provides a structured way to move from the beginning of a concept all the way through retirement of that project or product. The V part really focuses more on the technology development. And this is the NuScale system V model. It's very similar to what you would find if you just actually Google searched system V model. You get a lot of different charts that look very similar to this. And the idea is we often talk about the left side of the V, which is the system definition, requirements allocation, and derivation, where you start off where someone in the business says, hey, we have an idea, or you get from a project office, we had to do this big project or develop this complex product. And so you work to define that. You work to define the business requirements and the customer requirements. Once those are defined, then there's a handoff and integration with a design team. Start developing that functional design, that architecture, the system requirements and functions. Once that happens, you can start to move into preliminary design, or what's called high-level design. That's both from a broad perspective as systems are added to that system of systems. And then as you get deeper and deeper, you start creating lower level design artifacts there, going from 3 to 4. Obviously, all this is iterative between those 1 through 4 steps. But there comes a point where you start actually developing and testing hardware and making things. And then the right side of the V is after you start to build and how do you assemble these things, and how do you make sure that you're putting the system back together and you're building it and constructing it such that it's meeting the requirements and the design artifacts that you have on that left side. And you do that through validation plans and verification plans, unit test plans, and et cetera. So that right side is often called the product realization side, where you're starting to integrate and verify and validate your product is being put together and achieving your performance objectives. And then eventually move into startup commissioning. And then the development V model sort of ends at that phase, and you go into other operations and retirement lifecycle phases. But systems thinking is holistic, it's functional, it's logical, it's performance-based, and it really focuses on how the system should perform in the operating environment. And a system V model really provides a structured way with proven practices to move through that development cycle. Next slide, please. All right, looks like we lost some figure there, unfortunately.
Yeah, I'm sorry, Kent. This is the actual presentation. It's not the...
Oh, it might be animated. Can you click a couple times maybe?
Mm-hmm.
I thought we were working off the PDF.
Yeah.
Can you click?
There.
Yeah, it's just a little animated. I forgot. So the value proposition really for systems engineering is lower cost, shorter schedules. You can absolutely design a nuclear power plant the traditional way. If you could advance again, I think the value proposition really is by implementing some proven as systems engineering best practices, you can shorten that time and reduce the cost. Then the question is, well, how much? How much systems engineering does a project need to be successful for meeting the cost and schedule requirements of that project? And that's where Eric Honor had done a lot of research. If you go to the next slide, over the years, and he's got a great PhD thesis. Next slide, please. Thanks. Where he looked at a lot of mega projects. Now, I don't know every specific mega project he looked at. I know there was projects from large civil construction projects like dams, to large power plants, to city infrastructure, to aerospace. So it was just a large collection of projects over, like, a certain amount. I think it was like $1 billion or more. And looked at and investigated, did these projects finish on time and on budget? So what you see here is a chart from his thesis, and this is gets a lot of traction in the systems engineering world. And it talks about, this first one is schedule versus SE effort. So we have actual versus planned schedule on the vertical axis, which means that one is on schedule, and anything above that is behind schedule. So you can see most of the projects mega projects were behind schedule, some 3 times what the original estimated schedule was. There are definitely more than several that were on schedule, and there were a few actually that were beat the schedule. And then what he did is he looked at, picked apart their project plans and said, well, how much systems engineering effort was spent versus a percentage of program cost. And that's on the bottom there. And what he found was that there seems to be a sweet spot. Too little systems engineering effort, and you don't get the value. And too much actually can be too much of a good thing, actually. So on the right side, and the too much, for those projects that had, say, a high amount of systems engineering effort, they overspecified the problem quite a bit. Their requirement specifications were too restrictive. Their configuration management systems were too rigid that they weren't able to manage change very well. And although they spent a lot of money on those things, it actually didn't lead to much savings from a schedule perspective. So it looks like, I think in his thesis, 14-ish% plus or minus was the sweet spot. And there's some uncertainty, obviously, in that number for the percent of SE effort and total program costs. Next slide, please. Total, yeah, and this is the same concept, but then this is just the cost of the project. So there's the schedule and cost, and then you can see it's very similar, value proposition. It's about that 14% where you see some real value of systems engineering being able to control costs. Next slide, please. So we talked about how much, but now it's what Eric Honor also did was look at, well, and we'll get into a little bit later, what systems engineering is. And it's a broad discipline that has a lot of different sub-disciplines. And this figure here, I should have put the legend on the right where we have mission definition, requirements engineering, et cetera. But these two figures, what it tries to communicate is that it's those programs or projects that were successful, meaning from a cost perspective, they hit their budget. What was found was if they spent more time and money upfront on defining the project or mission purpose, they spent more time and money on technical leadership and management, and in general spent about that 14% on systems engineering overall, they did quite well. What I found is those programs that did poorly is if you didn't spend the time upfront to define the mission, define those requirements and goals for the project, what that leads is downstream into more effort for integrating those systems when you put them back on the right side of the V process, and more time and verification and validation because the requirements weren't written in a way that facilitated effective V and V. There was a lot of rework on the back end of the right side of that V process. And what you find obviously is it's cheaper to change paper than it is hardware. So if you're building things and you're going through and testing them to see if they work and meet your performance objectives and they don't, it's a lot more expensive to be changing and modifying real physical equipment than dealing with those issues on the design side. So it's, I guess, intuitively obvious, but this is some real data to back up those concepts of what is a successful systems engineering implementation and what is a poor systems engineering implementation. Next slide, please. So at NuScale, every design organization, a reactor vendor has specifications. They manage requirements. They do verification and validation. But not all design and product organizations consolidate that and put it into a structured, formalized program. And in the very early at NuScale, we did not. We had a lot of the elements of systems engineering, but we didn't have a quote unquote formal program. So we started doing that several years ago with some objectives. One is to ensure that all of our stakeholder requirements, not just regulatory, but customer, supply chain, all of our stakeholders, their requirements are identified early in the product development process, and they're decomposed and allocated to the appropriate SSCs early. So we definitely spent, as we stood up a more formal program, we spent a lot more time on capturing stakeholder requirements and then feeding them into the design process. This helps us increase the confidence in our project costs and schedule. If we write better requirements and they're more performance-based, then we have a lot more confidence than when we start to realize the product on the right side of the V. We start building and manufacturing that will meet the stakeholder needs that were defined up front. I mean, the basic idea is if you have a customer and you haven't defined what it is to have success to meet that customer need, and you haven't written that down, formally got it in the design process, you're trying to hit a moving target. So it was really important for us to nail down that target so that we can hit it and be successful with our customers. We also need to tailor it. You just can't take all the great best practices in systems engineering out there from INCOSE, which is the International Council of System Engineers, to the Department of Energy, DOD, IEEE, all the NASA, even the body of knowledge out there. We need to tailor it to our product lines and our business. And we spent a lot of time doing that. So, and for us to do that effectively, we needed to really, I think, and I didn't have a lot of slides on this, but really do a good job identifying and that the nuclear power plant is a collection of products, right? It's a single product, but it has a collection of products and they need to work well together. And the interface definition of those products is super important. So we spend a lot of time doing that. Next slide, please. So the first step is a standard, and that's why I put this here, because this is an ANS standards community of practice. I chair a couple of standards, and so I'm very a proponent of a standard setting the goal or the target. And so at NuScale, we have a systems engineering internal standard, and it sets the process requirements for our product management for all of our product lines. The scope of it really addresses system design, technical management and control, and product realization of our end products to our customers. It takes special effort to look at integration of specialty engineering disciplines. And what I mean by that is the nuclear industry has a lot of specialty engineering that have to work together, like PRA, radiological, component design, ASME. There's a lot of nuclear specific specialties that have to work together and that might have conflicting requirements or guidance. And so that was a really important aspect of our standard to address. One of the things is a note is it doesn't invoke any quality assurance program requirements. That is our quality assurance program is a NQA1 compliant program with a whole set of processes and procedures for that. Our systems engineering standard is a value added proposition, right? We're saying we can still design a quality safe plant using all of our NQA1 processes and procedures. And we will follow those, but applying a systems engineering standard to that process, we could probably, and we feel strongly, we can do that more cost effectively. So that's the idea of that standard. Next slide, please. So what's in that standard? We broke it into 3 areas. First is system design. The second is technical management and control. And the 5th is product realization. So our internal standard very much mirrors the guidance that is provided in ISO 15288, which is a internationally recognized systems engineering software and system standard. But that's very sort of high level. It talks a lot about how, or I say what to do, but it doesn't necessarily provide a lot of detailed guidance on how to accomplish those requirements that the standard provides. And then what we did is that we looked at, for providing some additional guidance and detailed in our internal standard, we looked to the NASA Systems Engineering Handbook, 2nd edition, for some additional guidance in some of these areas, and industry benchmarking, because NuScale is not definitely not the only reactor vendor that is implementing or has implemented systems engineering programs to date. So this standard covers the full entirety of that system V model. And these are the different technical areas and sub-technical areas that the standard provides guidance for. Next slide, please. So where are we? We issued that standard a couple of years ago and conducted pilots. Again, we had a lot of those existing processes because of a nuclear vendor. We were just created a standard to make them more efficient and effective. And to do that, we needed to conduct some pilots to figure out how to do that. We also formed a dedicated systems engineering team that lives within engineering. We developed what are called tailored systems engineering management plans for our different product lines. We did a lot of training. We also developed change management plans. So we still follow our NQA processes and procedures, but we're adding some value to that process with this standard. So there was some change, and that was important that we communicated that change and managed it effectively. And then we did some high priority infrastructure items like selection of product lifecycle management tools, model-based systems engineering tools, requirements management tools, and that kind of stuff. We're continuing to invest in systems engineering and expanding our training beyond engineering and design, executing our plans and tracking our progress against the standard and adjust as needed. Next slide, please. This is not a complete list. It's just for the formal systems engineering group within NuScale, what do they do? And when you look at that process chart, or that I showed in that standard, they do a lot. They help facilitate what we call stakeholder needs elicitation and validation process. We create something for our product lines called a product concept document that really defines at a high level what our stakeholders want the product to do and where it's going to be deployed and how it's going to operate. It's got cost and schedule requirements in it and key features. They also facilitate the technical solution definition at the highest level, from writing plant design specifications and top level product specs. They do product structure modeling, product lifecycle modeling, managing functional architecture. Another key thing on systems engineering approaches is managing the product structure. It's defining a product structure and having a digital representation of the plant through the entire life cycle, and supporting a virtual twin sort of a concept where there's a single source of truth. And the functional architecture and the structure of that is an important part of systems engineering. I'm not going to read through the whole thing, but it just gives you a flavor of all the important aspects of systems engineering at NuScale. All right, so what successful SE implementation? The first and foremost is tailoring the the program or the process to the need of the organization. I strongly feel there is no one size fits all when you're implementing systems engineering best practices. And the reason why is because, at least in a nuclear vendor, there's already a lot of systems engineering best practices, right? There's already design specs, requirements management and verification and change control boards and all that kind of stuff. So the idea is to look at the existing systems engineering processes and procedures and organization, and putting a dedicated team together that says, well, how can I make that better? How can I make that more efficient? And it was really having, when we stood up the program, listening to the internal stakeholders and listening to their issues, right? And saying, well, it's tough to do this, it's hard to do this. This works really well. And then tailoring our standard and our processes to meet the stakeholder needs. And then managing the change. You're not gonna change and have better processes overnight, and you have to plan for it. And so change management planning is super important. We also found that communities of practice like these are really critical in gaining wide, broad acceptance of new concepts. So I facilitated a systems engineering community practice internal to NuScale for almost a year, just to get out key concepts, value propositions, and why this kind of change is important to at least our company. Program requirements first, and then product-specific plans. It was important that we established a standard before we started diving into the product development teams. So again, from a standards perspective, we got to set the target, and then we can figure out how to meet that target. PLM and moving towards a data-driven design process, we thought was also key. Designing a nuclear power plant using documents and sort of a flat structure is just not effective, especially when you have multiple products and you're virtual across the world. And so having a product lifecycle management system and configuration process where there's a single source of truth, virtual twin, if you will, we thought was fundamentally had to happen to have successful systems engineering and just success as a reactor designer and a developer.
Kent, are we showing the right slide on the?
Oh, next slide. Next slide.
I have
next slide.
You moved.
I had forgotten to advance. I forgot to advance. I'm sorry.
Why don't you just catch up to where we should be? So.
Yeah, I'm sorry. Next slide. I apologize. I was switching the slides on my computer. So, gosh. Thank you for interrupting me, Prasad. I apologize to the audience.
Are we at the right place now?
Yeah, I mean, I'm going to give myself a second to take a break. And Pat, maybe you could go back one slide. And then I will just reemphasize that these are some of the responsibilities of the systems engineering group. Big list there. And we'll provide the slides, obviously, after the seminar today. Okay, and if you go to the next slide, please. And this is where I was talking about successful systems engineering implementation. The final point being having strong executive leadership sponsorship to make these changes was critical. And that's critical to all sort of changes with process changes within an organization. Okay, next slide, please. All right, this is the final slide, just summary and conclusions. So yeah, the research on the success and failure of mega projects, I showed the data from Eric Idle, it's a Monty Python reference, Eric Honor, really shows, and there's other lessons learned from other mega projects, that the right amount and the right type of systems engineering effort really can help to control costs, maintain schedules, and reduce risk. Reactor vendors, I think, and constructors are realizing these findings and are moving towards increasing their systems engineering efforts. I know we are, I know our partners are, and I've seen other reactor vendors do that as well. So we really believe that implementing these best practices are essential to our success. And we've spent considerable effort over the last 3 years really doubling and tripling down on that. Again, we've had systems engineering since the beginning, but now that we're formalizing it and putting dedicated resources on it, we're starting to realize those savings. This is just a market penetration or acceptance sort of curve, and I kind of track this every year at NuScale, where in 2019 we were down at the early adopters when we started the community, the systems engineering community of practice, when we were just kind of introducing the concepts, and we have made significant progress over the last 3 years, and we are into that late majority adoption at NuScale. So it's really, I think, encouraging to see that when I talk to folks out, obviously within engineering and outside of engineering at NuScale, they understand the importance of systems engineering and what it is and why we're doing it. And so we'll continue to invest in it and get those laggards there at the top, the top part of that curve real soon. So that's all I have, and I am happy to open up for questions. Thank you.
Thanks a lot, Kent. We do have a couple of questions on the chat feature of this. The first one is from Charles Martin. I don't know if that's Chip Martin, but anyway, the question is, your standard is...
That is Chip Martin.
Oh, okay. Hi, Chip. Your standard is based on a traditional V model. Do you encourage, permit, or discourage agile methods for software development?
Yeah, that's a great question. What we found is at a very high level, that V model helps us at sort of the plant level organize major life cycle phases, if you will. What we find is when we look into individual product lines, like in the INC world or in the control system discipline, they are following their own life cycle models. For the module protection system, because of its nature, they've chosen a waterfall model, which is more of the old-fashioned version, and that was submitted to the NRC and reviewed and approved. On the non-safety control system side, they're leaning towards more agile development processes. So the standard gives sort of like a high level, you should define a product lifecycle model and development model, but it provides the flexibility within our organization for the specific product lines to choose the best one for that product line.
Thank you.
Next question, Kent, is from Thorium Energy. It says, what about using an open blockchain to validate steps and have public contracts that can expedite things?
I guess I don't know quite what that means. It's intriguing, but I would probably need to know more to
I don't know if that's John Kutch. John, if you're on, can you explain what open blockchain is in this context?
Sure. Wasn't expecting to jump in here exactly, but it's a concept that we've been pushing in that blockchain isn't just good for Bitcoin, but it's an open ledger system, and it allows vendors and contractors to work together. And since it is a public ledger, it allows you to expedite acceptance, and basically it adopts the idea of sort of like the drawing is the contract or the CAD is the contract and other concepts like that. And the contract is sealed within the blockchain, and everybody knows what it is and when it's completed and when progress is made. I mean, there's a lot more to it, but the general idea is to just take some of these advanced tools that we have available to us to get big projects like this done quicker, you know, and keep engineering and contracts and fulfillment from being the bottleneck, because we all know that the real cost driver of any of these major projects is, you know, if it takes 10 years to develop a project, you're going to have 10 years of financing, and financing winds up being 40% of the cost of a project.
Anyway, Kent, you have a response? Otherwise, you know, if this is unfamiliar to you, we can move on.
Yeah, I'll just say a quick response. Like I said, an intriguing concept. I don't know enough about blockchain to probably comment on that. But I think some of the intent of that, we do. So when we went over to some of our benchmarking, especially with our partner Doosan over in Korea, who've been building power plants quite extensively in Korea and around the world, they have a product lifecycle management system that we adopted and are implementing, where all of our suppliers and our designers and manufacturers, we were so impressed that they were all working within the same tool. So whether it was the designer in this organization or the manufacturing person on the floor, they were literally looking at the same tool and looking at the same database. They just had a different view to do their job. And so blockchain sounds like a concept to facilitate that kind of interaction between suppliers and data transfer. So I don't think we're doing blockchain currently. We might do it in the future, but I think in concept, we agree we need to be using modern tools to manage the information effectively. So, question.
Okay. Next question. Andrew Clark asks, the nuclear industry and certainly the RIPB-COP utilize and leverage safety analysis and PRA to inform design and evaluate plant risk. Can you speak to how NuScale has incorporated safety analysis and PRA into your systems engineering process?
Yeah, they work in concert. So our risk-informed, performance-based principles and methods, if you will, fall under the subset, it falls under a number of systems engineering categories. I've actually mapped it before. It falls under decision-making, which is a systems engineering discipline. It falls under requirements definition and defining safety. It goes under systems integration and analysis when you're actually doing PRA. So they work together and they work in concert. And so I'd say the area where systems engineering, in my mind, and I think I presented onto this last year, was to effectively implement risk-informed performance-based methods. You need to have systems engineering best practices because that really facilitates all of the specialty engineering like PRA, like safety analysis, like defining requirements, like performance-based decision-making, all those key concepts. You need to have a systems engineering program really to do that effectively, in my opinion. So yeah, it's a fundamental necessity for effective RIPV implementation.
Okay, thanks, Kent. Next question from Kent Novotny. I hope I'm saying it right. To what degree are your suppliers fully integrated into the systems engineering efforts and approach? And can you comment on the degree to which control is centralized within NuScale versus a broader community of practice approach?
Yeah, I'll try and answer that as best as I can. We have partnered with folks and suppliers and that share our view of the importance of systems engineering, I would say, and managing it. So like one of our key partners is Sargent Lundy, and they have a very strong systems engineering program, and it meshes well up that. So Sargent Lundy is our architect engineer who takes the the product that we've designed to the next level, right? In terms of balance of site systems and balance of plant systems and working with the EPC. So we mesh up very well with our architect engineer from our systems engineering and data management perspective. Same with Doosan Heavy Industries. Again, we benchmarked with them. So not 100% of our suppliers are all on the systems engineering bandwagon, but we've gained a critical mass internally and with our main partners and suppliers, our key ones, that we're, it's our goal to then, push and implement these best practices through our supply chain as best we can going forward. So the other question was broader communities of practice. Yeah, I guess I'm not sure on that one. Do you mean having a systems engineering? If the question is, having a broader systems engineering community practice with our suppliers, I think it's a great idea. And that's probably going to be necessary for us to, move forward with them, if that was the question.
Kent, if you want, you can unmute and clarify if you feel you can get a better answer.
Yes, and yes, you did answer both questions. I appreciate that. Yeah, the second question was more one of managing the SE. In other words, you go to a broader community of practice, even though it's good to get ideas from all the suppliers being fully integrated. I imagine there's got to be some sort of centralized control, if you will, to keep the overall system engineering efforts somewhat focused and directed all in the same, so everybody's going down the same path. Was the point of the question.
Yeah, no, and we do that with a couple ways. We do that with systems engineering management plans on our product lines. So for each product line, which includes our roles and responsibilities and our supplier roles and responsibilities, we develop those systems engineering management plans to clearly identify, where our requirement specs ends and where theirs picks up, the data flow and information, what codes and standards they're going to be designing to and what we're designing to. So it's very important to create those management plans for those product lines so that everybody's on the same page. Now, to support that, because it is just a document, you need to have the tools and the data management tools to support that. So that's why we're working with our suppliers. We're trying to get them off of the, you need to print everything out, these big drawings, and you do eventually need to do that. But what is the single source of truth? Well, it's working in our product lifecycle management system. It's having good communication between their plant models and our plant models. So we first have to set the management expectations and the plans, but then we have to do a lot of work in doing the information management to ensure that we can meet the objectives of those plans.
Okay, thank you. We still have a couple of minutes. I'd say if anybody wants to ask a question now, you're welcome to. We're almost at the end. So I'll open it up to the floor if anybody would like to ask. Okay, I don't see any other questions. I just want to sort of summarize. I think in one of your slides, Kent, what clearly came through to me was that this is a way to sort of front load project risk. And you can be more confident about the outcome, if you do it right, if you use systems engineering properly right from the start. Is that
Prasad, I did have a question. Sorry.
Oh, okay. Sorry, go ahead.
So I was wondering if NuScale standard might be available and possibly could be adapted as an ANS standard.
I think the short answer is, unfortunately, no, it's not available. It is proprietary, but on the flip side is it's very closely mirrors ISO 15288. Which is an international standard. So if you were to pick up the NuScale standard and the ISO standard, you would see very similar language. So, and scope and content. So, and I would say the ISO one provides a lot better guidance and more detailed guidance. That's what, if folks are looking for a gold or a standard that is internationally accepted, they should be looking at, grab themselves a copy of 15288.
Did you feel like you had to make any significant changes relative to that standard to meet U.S. nuclear needs?
Well, that is another great question. We are a global nuclear vendor, and so it was doubly difficult because we needed to meet not only U.S. needs, but multiple international needs. We have quite a bit of efforts going on in Japan, Canada, and the UK right now, which have different flavors of regulations and standards. So when we developed our systems engineering standard, we had to consider a lot of different deployment areas. But no, because there is no US standard, right? That we had to really.
This is Don Spellman, Kent. I might add that Ralph Hill at ASME is developing, and his group and ASME people are developing an ASME systems engineering standard. And I'm not sure what the details of that progress is from Ralph, but he is on a couple of our committees. So it certainly would be an excellent opportunity to make sure that ANS and ASME are harmonized on the work that goes into that.
Yeah, Don, I'm actually on the working group with Ralph on that. So yeah, I think we will be better, interacting as we go forward. Okay, at this point, I think we're approaching the end. Kent wanted a couple of minutes early to finish up. So I'll just say at this point that, I think we have a candidate for the community of practice presentation in March. That will be also March 26th. And the subject is most likely to be risk-informed performance-based methods in ALARA, as low as reasonably achievable kind of decision-making. So I want to thank everybody for participating in today's session. I want to particularly thank Kent for taking the time to tell us all about, how they do things at NuScale. And I welcome others, who also are implementing such practices to come forward, and we will accommodate you on our community of practice schedule as soon as we can. So again, thank you all very much.